Now we called the magnetic field from a wire loop a dipole. I'd like to explain that terminology because it's very widely used across many areas of physics and indeed more generally. Let's look at gravity, electric fields, and magnetic fields. The simplest pattern is a monopole. So for gravity it would be an object with some mass m, and then you're going to get a gravitational field that's spherically symmetric and pointing straight in towards it. And that's called a monopole field. Electrically it would be something like either a positive or a negative charge, and you get an electric field that points radially outwards, obeying the inverse square law, so actually mathematically the same as for gravity. And that's an electric monopole, just either a stray positive or negative charge. Now for magnetic fields there is no equivalent. If you had a north pole all by itself it would have a field like this, but there don't seem to be any such things as stray north poles without a south pole attached, so you don't actually get magnetic monopoles. That's the simplest field. The next step up would be a dipole field. So let's say you had an object with a mass of plus m and a mass of minus m. Now that does not exist. There's no such thing as negative mass. As far as we know, even antimatter has positive mass. But if you did have this, you'd have a gravitational field that went something like this. But those don't exist. You do, however, have electric dipoles. This would be something like a positive charge close to a negative charge. And then you get field lines that go something like this. It's a very common and well-studied pattern. You get these very often from molecules. In a molecule, very often the positive charges and negative charges will be offset from each other. So, for example, a water molecule, the electron orbitals are not perfectly symmetric, and so you get the negative charge offset from the positive charge, and you get a dipole, which turns out to be of enormous importance in chemistry. And that's what a wire loop is doing. It's giving you exactly this sort of pattern of field. That's also what you get from a bar magnet with a north and a south. So that's a monopole, and that's a dipole. And in principle you can go to more complicated patterns, quadrupoles and octupoles and so on. These are done using the mathematics of so-called spherical harmonics. So this is a representation of a monopole. It's the same in all directions. These are dipoles, which is where you have positive at one side and negative at the other. And they can be in various orientations. And then you get more complicated quadrupoles, which can have more diversity. These would be equivalent to having 2 positive and 2 negative charges, or double wire loops or something like that. And then you'd have higher order poles, so octupoles or whatever it might call it. And in general, these can be used to explain any pattern on a sphere. So for gravity, you pretty much only have a monopole because there's no such thing as negative masses around there. You can get electric and gravitational monopoles, but you can't get magnetic monopoles as far as we know. There's no fundamental physical reason why you don't, but they just don't seem to exist in practice. For magnetic field, the dipole is the most common pattern, and most things can be built up of that. But if you have any arbitrary pattern on a sphere, you can build it up by sums of all these different things. So, for example, in quantum mechanics, the electron orbitals of, say, a hydrogen atom are just made up of combinations of these things. In cosmology, when we're trying to map the pattern of the microwave background across the sky, once again, we do a multipole expansion. We have the monopole, dipole, quadrupole, and so on, and add them up until we get the true pattern. You can explain the shape of planets and their tidal forces by expanding the Earth as a monopole, which should be a sphere, a dipole, which will account for the bulge around the middle of the Earth, quadrupoles, which will account for other distortions, and so on. So this is a very useful mathematical trick.